Hey, welcome guys. This is my welcome to my group theory lecture. And this time I'm going to talking about solvable groups. Solvable groups is important in the Galois theory. So I want to present my own version of notes, and I hope you guys subscribe to my channel. Okay, so settings that let me just define. This is a group G. So let's first define a commutator of x and y belongs to G. So definition of this commutator, two elements defined to be x, y, x inverse, y inverse. Okay, and you can define a so-called commutator subgroup. Okay, so you can define the commutator subgroup of G defined to be the group generated by x, y, x inverse, y inverse. Okay, so basically each element in this commutator group, or basically some people like to say it's derived group, is defined to be the product of this. Okay, so by definition, this will form a group. You can check by yourself, right? Because if you can prove that the inverse of this element just for example, inverse of this element will be just yx, y inverse, x inverse. And if you put x and y to be identity, then it gives you the identity. Okay, so you can prove this is group. Okay, so and this commutator group has some applications. For example, the famous results that the singular cohomology H1 is basically is pi1, the commutator of pi1. So okay, so this is the notation. So usually that the derived this commutator group define G prime denoted as G commutator G. Okay. Okay, so this theorem that we will use, and once we have this, then we can define solvable groups. So this theorem says that G prime is a normal subgroup of G, and G prime is the smallest. I think only this is important. Smallest normal subgroup. Smallest normal subgroup n of G such that G quotient n is abelian. Okay, so G prime is a subgroup of G. Not only that, this G prime is the smallest. Basically, it's the smallest subgroup. Smallest subgroup n, such that for all the subgroups which n is a normal in G and G quotient n is abelian, this G prime is the smallest one. Okay. Okay, so this idea means that if, so basically, let me just write. So this means that if n is a normal subgroup of G and the G quotient n is abelian, then you can say that G prime is a subgroup of n. Okay. So okay, so G prime is normal. So this okay. So let's check that G prime is normal. I think it's not difficult, right? Basically, you can check that, let's say, right, so you can write x equals to any element x belongs to G prime as a C1 up to Cn. And each element of Ci looks like a xi, yi, xi inverse, yi inverse. Yeah, okay. So if you take a inverse, then you become a C1 A inverse, A C2 A inverse, up to A Cn A inverse. Okay. And so let's take A belongs to G, and we need to prove that we need to check that this guy is still in the this guy is still right as a commutator, right? But this is trivial, right? Because this A, you can check that this A C1 A inverse will be just A x y x inverse y inverse A inverse will be A x A inverse A y A inverse A x A inverse inverse and A y A inverse inverse. So basically, if you sandwich an A inverse with the commutator, then still be a commutator, right? So this guy is still commutator, commutator to the commutator. So this final results, this element still belongs to G prime. Okay, so which proves that G prime is normal? Okay, so G prime is normal. Okay, so now let's check. So now let's prove another part. So basically, let's consider that x inverse y inverse belongs to G prime for every x, y belongs to G. So which tell you that G prime x, y equals to G prime y x. And the G quotient G prime is abelian. Okay, this is a definition, right? Because any yx commute with the G prime. Okay, so which tell you that this G prime is abelian, which tell you that this G quotient G prime is abelian. Okay. Okay, so now I want to prove that if you have another normal subgroup n such that G quotient n is a normal G quotient n is abelian, then the n must be G prime must be a subgroup. Okay, so let's consider somebody give you this n is a subgroup of G and such that G quotient n is abelian. Which tell me that nxy equals to nyx. So which tell me that xy x inverse y inverse is n. So which tell you that G prime is a subgroup of n. Okay, so this is a proof. Okay, so now let's define solvable groups. Okay, so definition. So when we see I say that G is solvable, basically it means that you can find a so-called commutator series. So there is a commutator series. Maybe that's this. So G is solvable means that you can find the following series. The following series, basically you can find a normal subgroup of n, let's say n1, or basically G1, and another G2, which each G1 is normal subgroup G, G2 is normal subgroup of G1 and the G3. Okay, and up to somewhere maybe GK. Okay, which is identity, such that the GI quotient, let's call this G0. So GI quotient GI minus 1 is abelian. Okay, so basically you can find a series that that each quotient is abelian and keep going until you go to the trivial group. This is called a solvable. Okay, so the trivial example is that when your group G is abelian, so if G is abelian, then G is solvable. Okay. Okay, so usually it seems like that computing define check whether a group is solvable is not very easy task because you need to do all the commutator. Okay, but this is actually not true. So this is the theorem that people like to say. So basically, you can construct another series from G to normal subgroup of this G prime and go to the G prime prime, right? So this is all the commutator group, right? So you can construct this kind of series. Okay, the theorem says that G is solvable if G of R, which you do some commutator, is 1 for some R. Okay, so proof. Okay, so this direction is trivial, right? Because suppose you have a commutator group, then which the commutator one by one will give you it's already become one example of the series. Okay, so this is trivial. Okay, how about this part? So this part means that you need to prove that if G is solvable, basically you can, if you have this kind of series, then you can argue that the derived group must terminate. Okay, now this proof is also trivial, right? The reason is that suppose you got this kind of series, then G quotient G1 is abelian, right? Which means that G1 will cover the commutator group G prime. Okay, and the G1 quotient G2 is abelian, right? So that means if you take the commutator group again, your G prime double prime will be the subset, right? Well, this G double prime will be a subset of G2. Okay, and you keep going, right? So finally, your GK becomes the identity, which your G of K will become identity. Okay, so this is the proof. Basically, you just use the previous lemma in the multiple times, and you get the results. Okay, so let me just write down some fact, and I want to prove that the famous result that the S5 is not solvable, or basically Sn is not solvable. Okay, so this is a fact, some fact that you can view as exercise. I think it's very simple. So just write down the definition. Okay, the first one is that so every subgroup of solvable group is solvable. Okay, so this is a nice property. Okay, the second is that the quotient group of solvable group is solvable. Okay, the third is that if G quotient n, so basically let's say n is a normal subgroup G, if G quotient n is solvable and n is solvable, then G is solvable. Okay, so this is the third one, may be a little bit technical, but you can check the proof. Okay, so theorem that I want to prove, which is very simple. So G to a P to if you get prime power n, then G is solvable. Okay, so this proof is very simple, right? Because when n less or equal to 2, then by the simple group classification that G is P squared and G must be abelian. Okay, so G is solvable. Okay, and then for n greater than 2, that I can do by induction. So by induction, and the Seedle theorem, and in the simple group classification results, right? I can take the center of the G. When G is P to the n, this center group is must be non-trivial, right? But your C of G is normal in G, so Z of G is also some prime power, let's say n minus k for some k. So this guy will be normal. This guy will be solvable by induction, and this guy will be normal. So by the previous theorem, the previous fact 3, that we know that this G of prime power n is solvable. Okay, and this is a theorem that I'm not going to prove in this video, but I will prove it in the future. It's Bird's-eye theorem, which is a very famous result. So if your G is 2 prime power to P to n or Q to m, the products where P, Q are primes, then G is solvable. And this proof, usually you need to use the representation theory. You need to use the group representation. Okay, so finally, I want to prove the famous results. So where we will use in the Galois theory. So G is Sn greater or equal to 5 is not solvable. Probably this is the first non-trivial proof that you can try to prove. You want to prove that this is not solvable. Okay. So let's see the proof. Okay, so let's only consider n. Let's only consider n is 5, because you can do a simple math to say to first fix the element. So if you prove that S5 is solvable, it's not solvable, then you can easily get S6 is not solvable, and keep going. Okay, but basically, let's consider this, and I want to claim what? I want to claim that okay, so there is a lemma that I want to prove. So this lemma says that if n is a normal subgroup of G equals Sn, and then which so lemma is that if n is a normal subgroup of G equals Sn such that n contains all 3 cycles, Okay, so basically you can, if you notice this n is just something which is maybe a n, right? So this is your imagination, right? But my proof is just only say that if n contains every 3 cycles, then the commutator of this n prime must contains all 3 cycles. This is just one example. Because n can choose to be Sn or An, right? But basically, I just say that if n contains all 3 cycles, then its commutator must be contains all 3 cycles. Okay, so proof just some brute force computation. For example, if you take A to be 1, 2, 3, then B to be 1, 4, 5. Okay, and you want to compute this, right? So the A inverse is 3 to 1, and then 4, 5, 1, 4, 5 for 1, 1, 2, 3, 1, 4, 5. And you want to compute. So this is a simple compilation, and you need to read from left to right. So 1 go to 2, and 2 go to 3. Okay, so 1 go to 3. Sorry. 1 go to 3, and 3 go to 1, 1 go to 5. Okay, so you see 1 go to 3, 3 go to 1, and 1 go to 5. Okay, so sorry, 1 go to 4. Okay, so your result will be 1 go to 4. Okay, then you can check that 4 will go to 1, 4 go to 2, 2 to 1. So this is 1, 4, 2. Okay, and right, so this means what? So suppose let's say AB belongs to A. Okay, so this commutator must be in n prime, right? So this must be in n prime. Okay, so which tell you that okay, so suppose I have this. Let's say for any pi, for any transformation pi belongs as n, then the pi inverse 1, 4, 2 pi must be inside the n prime. The reason is that this guy is a commutator inside n prime. So if you sandwich of this pi inverse 1, 4, 2 pi become pi inverse A inverse B inverse AB pi, this guy become n prime. Okay. So you just choose for every pi, right? For every pi, you just choose, let's say you can choose pi 1 map to I1, pi 4 map to I2, pi 2 map to I3, and the I1, I2, and I3 are distinct integers. So I1 and I2 are distinct integers. I3 are distinct. So you take any distinct in 3 cycles, right? And then you put this in. But this will tell you what? This will tell you that this n prime contains every 3 cycles, right? Because you can choose pi to be such, satisfy this relationship. Okay. Then this guy, this pi inverse 1, 2, 4 pi, if you take, it will be just I1, I2, I3. Okay, so which tell you what? Tell you that which tell you that n prime contains every 3 cycles. Okay. So that's it, right? So an n prime contains every 3 cycles. So this is the lemma. Okay. So now we can prove. So let's say we can prove the results. Basically, Sn is not solvable. Okay, the reason is this, right? So you just take n, this original n, right? Because originally I just say n is a subgroup, some subgroup of G, which is Sn. Then you just take n to be Sn itself. So just take G to be Sn itself. So which tell you that this n prime still contains all the 3 cycles, right? So n prime contains all 3 cycles. Okay, so if you know the fact that an is generated by all 3 cycles, right? But basically you don't need to learn about the definition of an, then you can also do this. So n prime contains every 3 cycles, right? And the n double prime still contains all the 3 cycles. N triple prime also contains every 3 cycles, right? So never terminate. Okay, so Sn is insolvable, not solvable. Okay, so this is the results that I will use in the Galois theory. So I just make a very short video about the solvable groups, and there are many other interesting aspects of solvable groups, like Hall theorem, or a lot of many beautiful theory about solvable groups. And I will talk in maybe in the future.